I grew up playing video games about shooting lasers at asteroids, and now it's my job to shoot lasers at asteroids. It never stops amazing me. My name is Tim Haltigan from the Canadian Space Agency, and I'm the Canadian Mission Manager on Osiris-Rex. I'm responsible for the overall operations of the OLA instrument and also responsible for coordinating the contributions of the Canadian science team. So Osiris-Rex is an international collaboration led by NASA that is a mission to go to an asteroid named Bennu, capture a sample of it, and bring it back to Earth so we can understand a little bit more what it's made of. Understanding the shape of asteroid Bennu is going to be absolutely fundamental to understanding the geology and putting it in context. The other reason you really need to understand the topography extremely well is that when we're going in to take a sample, it's a very, very fine measurement. And so if you're coming in, you've got the sampling head at the end of this arm that has to come in perfectly square to the surface. If you don't understand shape, sort of at a 30 centimeter scale, you're not going to be able to collect a sample. So OLA, or the Osiris-Rex Laser Altimeter, is an instrument on the spacecraft that has two lasers inside of it, and it acts sort of like a 3D scanner. OLA is going to create a three-dimensional map of the entire asteroid Bennu at a resolution of about 1 point every 7 centimeters. This operates very similar to a radar. However, instead of using a radio wave, it uses light. And so by measuring very accurately how long it takes for that laser pulse to go out and bounce off a surface and come back, you can measure a very accurate distance away from the spacecraft. The reason we have two different lasers is that we have to measure the asteroid from different distances away from it. So the high-powered laser we can use from about 7 kilometers into about 1 kilometer away from the asteroid. The low-energy laser we can then use from 1 kilometer and inwards. And so as we get closer and closer to the asteroid, we can make a lot higher resolution maps and understand the shape of certain regions even better. The Canadian Space Agency contributed OLA to this mission for a number of reasons. First is that it allows Canadian scientists to have access to astromaterials for the very first time. So these are the first samples that are coming back on a sample return mission that Canada is going to own a portion of. The second reason is that it really highlights the expertise of Canadian scientists and engineers, and so the ability to contribute something like this to a mission as exciting as Osiris-Rex really means a lot to the agency and to Canada. If you ask anyone that's ever built a flight instrument for space, they'll tell you all kinds of fun stories about the challenges they've had doing it. When you're building an instrument, you have an original design, you build a prototype, and you test it. What you want to do is something called test as you fly. Flying an instrument in space is a horrible place. So with flight instruments, what you need to do is put them on a table and shake them really hard to make sure that they're going to be able to survive the launch. You need to bombard them with radiation to make sure your electronics are still going to work. You need to put them in a chamber and completely evacuate it to make sure that everything still works when you're in a vacuum. In the end, ultimately what you have is an extremely robust system that you're confident that when you strap it to the side of the spacecraft, launch it, and fire it in space, it's going to work beautifully. I am incredibly excited to actually see what this asteroid looks like. When we get there and we see the first images and generate that first shape model, I think it's going to surprise everyone.